Somewhere in the constellation of Orion, a star that has burned for nearly 10 million years is behaving in a way that has never been recorded in human history. Astronomers did not expect this. The equipment was not built to find this. And yet, across observations from the James Webb Space Telescope, the Hubble Space Telescope, and ground-based observatories working in coordination, a pattern has emerged that some scientists are calling unprecedented, and others are calling a warning. Not a warning of danger to Earth, we're far too distant for that, but a warning that one of the most famous stars in our night sky may be entering the final unstable chapter of its existence. What follows is not speculation dressed up as fact. It is the real sequence of discoveries, stitched together, that has quietly turned Betelgeuse from a curiosity into one of the most closely watched objects in the observable universe. Let's start with the question nobody in the mainstream coverage is really asking. Why does a single red star, sitting in the shoulder of Orion, over 500 light years away, keep making astronomers nervous enough to reschedule telescope time for it? Why does a star that has existed for millions of years suddenly get treated like it might do something dramatic within our lifetimes? That question alone should stop you. Because stars do not usually behave on human timescales. They live and die across spans so vast that entire civilizations rise and fall without a single meaningful change happening to them. Betelgeuse is different, and the more data comes in, the harder that difference becomes to explain away. Here is where the story actually begins, and it begins with something astronomers do not say lightly: instability. Betelgeuse is what's known as a red supergiant, a star in the final major phase of stellar evolution, and by every measurement we have, it has burned through most of the hydrogen fuel that once made it stable. Think about what that actually means for a moment. A star spends the vast majority of its life in a kind of equilibrium, a tug-of-war between the outward pressure of nuclear fusion and the inward pull of its own gravity. For most of Betelgeuse's life, that balance held. But stars like this one do not fade quietly. As the fuel runs low, the internal engine becomes erratic. The outer layers swell to grotesque proportions, and the star begins a slow, violent unraveling that can take anywhere from centuries to mere decades, depending on what's happening deep inside a core we cannot directly see. And this is where the scale of the thing should actually hit you. Betelgeuse is not just big, it is almost incomprehensibly big. If you removed the sun from the center of our solar system and replaced it with Betelgeuse, its outer atmosphere would swallow Mercury, Venus, Earth, and Mars without resistance. And depending on which pulsation phase you caught it in, it could reach out toward the orbit of Jupiter. Sit with that. A single star so large that our entire inner solar system would exist inside it like a marble dropped into an ocean. This is the object astronomers have been staring at, and this is the object that just gave them something they did not expect to see. Now here's where it gets worse. In late 2019, Betelgeuse did something that had never been documented in the era of modern astronomy. It began to dim, not slightly, dramatically. Within a matter of weeks, one of the 10 brightest stars in Earth's night sky lost so much of its visible brightness that casual sky watchers noticed the change without even using a telescope. The story exploded across science media within days. Was this the beginning of the end? Was Betelgeuse about to go supernova in real time, becoming the first naked-eye supernova visible from Earth in over 400 years? For a few tense months, even professional astronomers could not rule it out. Read that again. A star that professionals could not confidently explain, behaving in a way that broke from centuries of recorded pattern, dimming so severely that its position in the sky's brightness rankings actually dropped. This wasn't a rumor. This wasn't a clickbait headline detached from reality. This was documented, measured, and confirmed by observatories around the planet, all pointing at the same conclusion. Something inside, or on the surface of, Betelgeuse had changed. The explanation that eventually emerged was almost as dramatic as the fear itself. Researchers determined that Betelgeuse had experienced what's called a surface mass ejection. Essentially, the star violently expelled a massive chunk of its own outer surface into space. To put the scale of this in perspective, astronomers estimated the ejected material carried away roughly 400 billion times the mass typically thrown out in a single coronal mass ejection from our own sun. That is not a typo. 400 billion times. As that expelled material moved away from the star and cooled in the cold vacuum of space, it condensed into a dense cloud of dust, largely composed of silicate compounds, that drifted directly into our line of sight and blocked a portion of the star's light from reaching Earth. Betelgeuse hadn't dimmed because it was dying in that exact moment. It had dimmed because it had just violently shed part of itself, and the debris was blocking our view. But here's where you have to stop and really absorb what that means. A star does not casually blow off a piece of its own photosphere, the visible surface layer, without something deeply abnormal happening beneath it. Scientists believe the trigger may have been an enormous convective plume, a churning upwelling of hot plasma more than 1 million miles across, rising from somewhere deep inside the star's turbulent interior. This plume is thought to have disrupted the normal convection cells that drive Betelgeuse's regular pulsation cycle, generating shock waves powerful enough to physically tear away a portion of the star's outer skin. This is not the kind of event associated with a stable, aging star quietly waiting out its final centuries. This is the kind of event associated with a star whose internal machinery is beginning to break down in ways we do not fully understand. And this is where everything changes, because the story does not end with the great dimming, it escalates. For decades, astronomers had recorded Betelgeuse's primary brightness cycle, a rhythmic pulsation that repeats roughly every 400 days, the star swelling and shrinking like a slow cosmic heartbeat. But there was always a second, stranger rhythm buried in the data, a longer, less understood variation stretching across roughly 6 years, a pattern astronomers had struggled for over a century to explain. What was causing it? No one had a confirmed answer. Some suspected internal convective cycles, others speculated about hidden structures. The truth remained hidden until new observational campaigns using the Hubble Space Telescope, combined with nearly 8 years of continuous monitoring data and ground-based follow-up, uncovered something almost nobody was expecting. Betelgeuse has a companion, not a planet, not a passing asteroid. A second star, small, faint, and until recently completely undetected, locked in an orbit so tight that it is believed to be skimming directly through Betelgeuse's outer atmosphere as it circles. Astronomers have given this companion a name, Siwarha, and according to the research team at the Center for Astrophysics, this companion star appears to be carving a visible wake through Betelgeuse's extended atmosphere as it moves, generating a dense trailing stream of disturbed gas, not unlike a boat cutting a path through water. Except the water in this case is the outer layer of a star hundreds of times larger than our Sun. This companion, researchers now believe, may be the long-missing piece explaining that mysterious 6-year secondary variation that had puzzled observers for generations. Think about what that means. For over 100 years, one of the most studied stars in the night sky was hiding a companion in plain sight, so close to its monstrous host that it is physically brushing through the outer layers of Betelgeuse's atmosphere with every orbit. This wasn't found through casual observation. It required years of painstaking high-precision monitoring, cross-referenced against ground-based data before the signature became undeniable. The announcement was made public at a major meeting of the American Astronomical Society, and the research has been accepted for publication in a leading astrophysical journal. This is not internet speculation. This is confirmed, peer-reviewed science entering the public record in real time. But what does a hidden companion star actually change about Betelgeuse's fate? Here's where the tension deepens further. A companion star orbiting this close to a red supergiant does not simply coexist peacefully. Its presence can influence how mass is lost from the giant star's surface, how material is redistributed through the extended atmosphere, and potentially even how internal instabilities manifest observationally. In other words, Siwarha isn't just an interesting discovery sitting quietly in the background of Betelgeuse's story. It may be actively shaping the very behavior that has made this star so unpredictable in the first place. What was once treated as a mystery unique to Betelgeuse's internal physics may in part be the fingerprint of a smaller companion star locked in a slow, dangerous dance with a dying giant. And this is where the James Webb Space Telescope enters the picture and the way its role is most often discussed. While Hubble's long baseline monitoring helped reveal the companion's gravitational and physical influence, Webb's infrared instruments have been used to probe something else entirely: the material actually ejected from Betelgeuse's surface during and after its violent outbursts. Infrared observation matters here because dust, the same dust responsible for the great dimming, radiates heat that is largely invisible in ordinary visible light, but glows clearly in the infrared spectrum. Webb's ability to cut through obscuring dust and directly trace outflowing material has allowed researchers to follow the ejected matter as it moves away from the star, cooling and dispersing into the surrounding interstellar environment. This is not a single dramatic image capturing a countdown clock. It is a continuous, evolving data set. And every new observation adds another layer to a picture that keeps getting more complicated, not less. Here is where most casual coverage of this topic gets it wrong, and where the real story diverges from the headlines. What most people are not seeing is that no single observation, not the great dimming, not the companion star discovery, not the infrared plumes captured by Webb, proves that Betelgeuse is about to explode tomorrow, next year, or even within our lifetimes. Supernovae cannot be predicted with that kind of precision. Even with the most advanced instruments humanity has ever built, we cannot look at a star's surface and generate a countdown. What we can do is observe patterns. And what those patterns increasingly show is a star whose internal stability appears to be degrading in ways consistent with the final phases before core collapse. Phases that, on cosmic timescales, could still stretch across tens of thousands of years, or could, in rarer and more dramatic scenarios, be measured in centuries. This is not chaos. This is a system entering a phase of change, and every fragment of new data is a piece of a puzzle astronomers are racing to assemble before the picture completes itself. So let's talk about what actually happens if, or when, Betelgeuse goes supernova, because the scale of that event deserves its own moment of weight. And when a red supergiant of this mass reaches the end of its fusion process, having exhausted the ability to generate energy through progressively heavier elements up to iron, the core can no longer support the crushing weight of the star above it. In a span of mere seconds, the core collapses catastrophically, triggering a shockwave that tears through the outer layers and detonates the star in one of the most energetic events the universe produces. If Betelgeuse goes supernova, the resulting explosion is expected to become extraordinarily bright in Earth's sky, potentially rivaling or even briefly surpassing the brightness of the full moon, visible during daylight hours for a period of weeks, before gradually fading over following months. For a distance of roughly 500 to 600 light years, this presents no danger to Earth. We are far outside the range where a supernova's radiation could meaningfully harm our planet's biosphere. What we would receive instead is the greatest, safest front row seat to stellar death that modern astronomy has ever documented. A live, close-range case study in how heavy elements, the very building blocks of planets and life, get forged and scattered across the galaxy in the final violent breath of a dying star. But here's the tension that keeps scientists cautious, and it's worth sitting with. Every signal Webb and Hubble have picked up, the surface mass ejection, the dust formation, the hidden companion disrupting the outer atmosphere, the erratic brightness patterns that no longer fit cleanly into decades-old models, fits the general profile of a star under increasing internal stress. None of these signals, individually, proves an imminent explosion. But collectively, they represent exactly the kind of behavior astrophysical models predict we should see as a red supergiant edges closer to the final stages of its life. The real story is not a countdown clock ticking toward a specific date. The real story is that, for the first time in recorded human history, we have the instruments sensitive enough to watch a nearby massive star behave abnormally in near real time. And every data set coming in adds new uncertainty to old assumptions. And this is where the power shift in this story becomes clear. For most of scientific history, our understanding of how stars like Betelgeuse die came entirely from theoretical modeling and from studying supernova remnants. The aftermath, not the lead-up. We inferred what happens before a star explodes by working backward from what was left behind. Betelgeuse changes that equation entirely. For the first time, humanity may be watching the actual lead-up to a nearby supernova unfold in observable, documented incremental steps. The companion star, the surface eruption, the dust formation, the shifting brightness cycles, these are not disconnected curiosities. They may be the earliest observational record ever compiled of a massive star's true final chapter, assembled not after the fact, but as it happens. Think about the scientific stakes riding on that. Betelgeuse sits close enough and is massive enough that its eventual supernova is expected to become one of the most thoroughly studied astronomical events in human history. Every instrument on and around Earth capable of observing it will almost certainly be turned toward Orion the moment signs of an imminent explosion are detected. And there is genuine scientific debate over whether certain neutrino or gravitational precursor signals might give astronomers a narrow, precious warning window measured in hours before the visible light of the explosion even reaches us. That's the real prize buried inside this story. Not fear, not spectacle. The possibility of directly observing, for the first time in modern scientific history, the true final moments of a star's internal collapse before the shockwave breaks the surface, a data set that could rewrite entire sections of stellar physics textbooks. But let's slow down again, because there's a version of this story that gets exaggerated, and a clear-eyed account has to resist that pull. According to informed astrophysical consensus, not internet speculation, but the actual published position of the researchers working on this, there remains no confirmed evidence that Betelgeuse's explosion is imminent in any meaningful human time frame. The Great Dimming Event, dramatic as it was, is now understood as a surface phenomenon, not a core collapse indicator. The companion star discovery, groundbreaking as it is, explains long-standing puzzles about brightness variation rather than confirming an accelerated death spiral. Even the infrared signatures Webb has captured of outflowing material are broadly consistent with the kind of mass loss red supergiants experience over long stretches of their late-life evolution, not necessarily an emergency signal. And yet, here's the part that keeps this story alive, keeps astronomers checking their instruments, keeps this topic resurfacing again and again. Uncertainty itself is the story. We genuinely do not know how much time Betelgeuse has left. Estimates that once comfortably sat at perhaps 100,000 years have, in the wake of these newer discoveries, been narrowed and debated within the scientific community with far more urgency than a decade ago. Some researchers now openly discuss scenarios measured in mere centuries, not because of confirmed evidence pointing to an immediate explosion, but because the newly observed complexity of the system, a hidden companion disturbing its atmosphere, violent surface ejections, reshaping its outer layers, and brightness behavior that no longer fits older predictive models, means our old assumptions about Betelgeuse's remaining lifespan were built on incomplete information. And incomplete information, when the object in question is one of the closest potential supernova candidates to Earth, is not a comfortable place for science to sit. Here's another layer. Most casual coverage skips entirely. Betelgeuse isn't being studied in isolation. It has become something of a proving ground for how modern astronomy coordinates across instruments, how a ground-based discovery, a Hubble monitoring campaign, and Webb's infrared capability can be stitched together into a single evolving narrative about one star's fate. This is a preview of how astronomers will study future stellar death events with a level of instrumental precision that simply did not exist a generation ago. Betelgeuse is, in a very real sense, a live rehearsal for humanity's first fully modern, fully instrumented observation of a nearby massive star's final act, whenever that act actually arrives. So where does that leave us? What most people watching this unfold online want is a clean answer. Is it going to explode or not? And when? Science, frustratingly and honestly, cannot give that answer with certainty. What it can give is this. Betelgeuse is behaving in ways that break from over a century of recorded pattern. It has violently shed a portion of its own surface in an event unlike anything documented before in a star this well studied. It has revealed a hidden companion star whose presence appears to be actively shaping its atmosphere in its most puzzling brightness cycles. And it continues to emit infrared signatures of outflowing material that researchers are still working to fully interpret. Individually, none of these facts confirms an imminent supernova. Together, they paint the picture of a star under genuine escalating internal stress, the kind of stress that eventually ends in one of the most powerful explosions the universe is capable of producing. And that brings us to the uncertainty this story has to end on, because pretending otherwise would betray what the actual science tells us. Nobody, not the researchers publishing these findings, not the teams operating Webb and Hubble, not the observatories monitoring Betelgeuse night after night, can tell you with confidence whether the star we're watching right now will still be there, quietly pulsating in Orion's shoulder 1,000 years from now, or whether the light currently leaving its surface tonight is already unknown to us, racing toward Earth carrying news that the star no longer exists in the form we've always known it. Because remember, Betelgeuse sits roughly 500 to 600 light years away. Whatever is happening to that star right now at this exact moment will not be visible from Earth for centuries. Everything we are studying, the dimming, the companion, the ejected mass, the infrared plumes, is already old news by the time it reaches us. Betelgeuse could have already gone supernova. The light of that explosion could already be crossing the vast emptiness of interstellar space, headed toward us, and we would have no way of knowing until the moment it finally arrives. Sit with that for a second. Every telescope currently trained on Betelgeuse is, in a very real sense, staring into the star's past, trying to read clues about a future that may have already happened. That is the strange, unresolved tension sitting at the heart of this entire story. A slow-motion mystery where the answer may already be sealed in transit across the galaxy, arriving on no schedule we can predict, revealing itself only when it chooses to. So the question isn't really whether Betelgeuse will die. Every star does, eventually. The real question, the one that keeps astronomers checking their instruments night after night, the one that keeps this story resurfacing across every major observatory's briefing notes, is whether we are witnessing, in real time, the opening chapters of the most significant nearby stellar death in recorded human history, unfolding in front of instruments finally advanced enough to actually document it as it happens. Or whether Betelgeuse, true to its long and confusing history, will simply settle back into its rhythm, dim and brighten for another few centuries, and let this entire moment fade into just another false alarm in a long list of them. Either way, something is different this time. The data confirms it. The instruments confirm it. And whatever Webb and Hubble capture next in the skies above Orion may end up being remembered as either the most anticipated non-event in modern astronomy, or the first real-time record of one of the greatest cosmic events a human civilization has ever been alive to witness. We are watching. We just don't know yet what we're actually watching for.